Good morning, everyone. So we'll start our session. First speaker is Rouven Frassek from Modena and Reggio Emilia. Oh, that sounds very tasty. Who's going to speak about boundary-driven q-Hahn processes.
Yes, thank you. So, yeah, indeed, I'm from Modena, where my office is, and so the university is shared between two cities, Modena and Reggio Emilia. So that's, but in Reggio Emilia, more the engineers, I would say. So thank you to the organizers. I'm enjoying this workshop or this program here very much. I've been already here for last week as well, and can get used to this place. It's very nice with the swimming pool. So I talk about this the relation between non-compact spin chains and integrable particle systems, stochastic particle systems in continuous time. And so the title was a bit different in the program, but so I decided to give a bit more introductory talk since there was not much about ASAP or something like that before now, since this moment. Right, so this is work that I started with Christian Jardinat and Jorge Kurchan in 2019, and then we developed this in several directions, and this I would like to present to you. So if there are questions, please interrupt me. Good. So this is the outline of the talk. First, I give this quick review of integrable simple exclusion models, the ASAP and the SAP, which are the key examples maybe. Then I discuss the quantum inverse scattering method, how these models can be treated or how they fit into this quantum inverse scattering method. This is something that we have already also saw in the last week, sort of, these lattice models. And then I come to this identification of these non-compact spin chains with stochastic particle processes. So there will be several examples. There will be the XXX spin chain, so the rational one, which has symmetric hoppings. This we call the harmonic process. And then there will be the asymmetric one, which is called the q-Hahn process, which corresponds to this XXZ spin chain with the asymmetry parameter Q. And then what we will do is to introduce boundary reservoirs for these type of processes. And then in the last part, I will show you how to actually compute the steady state of those models and how to map them to equilibrium. And then I give you an outlook. Okay, so simple exclusion models. Most famous stochastic particle processes are the ASAP and the SAP. I will be fast here anyway. So it's the nearest neighbor hopping model on a chain of n sides. So the sides can be either occupied or be empty. So there's at most is allowed for one particle per side. And then you can study this model with closed periodic or open reservoirs. What is what I mean by this? Boundary conditions. So here we have reservoirs at the end of the two ends of the chain, and with certain rates, alpha, gamma, beta, delta, we insert or extract particles, and the rates for the left and the right hopping are R and L. Okay, and if R and L are equal to 1, then this is the so-called SAP model, and this model is integrable, and there are some great reviews that I can here cite, so Derrida, Schütz, and many others. Right. So how to describe this process? It's described by a Markov matrix M. And this Markov matrix M is the following. So we have like a nearest neighbor interaction, W, or omega. And then there are the boundary terms, B1 and Bn, that are responsible for these reservoirs. So we see here that B1 contains these alpha, gamma, Bn contains delta, beta. And then the nearest neighbor hopping here comes from this 4x4 matrix that has this L and R inside. Okay, so and the property of this Markov matrix is that the sum over the columns or rows, depending on your conventions here, vanishes, and that it's important that you also have like only positive rates, so the off-diagonal entries should have opposite sign to the diagonal ones. Yeah, good. So how does this identification work with the XXX and the XXZ spin chain? It's quite easy. So the Hamiltonian of the XXZ spin chain is related to the Markov generator on the previous slide for some particular choice of parameters just by a similarity transformation here. So there's a similarity transformation which is slightly non-local that relates to the Markov generator. And then, okay, so this is the master equation which dictates time evolution of the probabilities in the configuration at time t of the process. So this is then governed by the Markov matrix. And once you have this identification, then you can use a lot of machinery that is available for these integrable systems, so coordinate beta ansatz, algebraic beta ansatz, and also representation theory that has been studied, and maybe also separation of variables and what else there is. Okay.
Can I ask a question? Sorry, so H, on the previous slide, H was Hamiltonian of XXX or XXZ?
XXZ, yes.
And what S was? What was S? Yeah.
S is a similarity transformation that is diagonal. Mm-hmm. It depends on the site index. Mm-hmm. And then you have this relation. Right. I didn't give it explicitly, okay. Sorry, it's not very complex.
On the previous slide, it was not M that you were writing H, right? The first line above.
This one?
Yeah, that was H.
This is, minus M transpose there. This is H.
I thought there was a similarity transformation.
Ah, okay. So here, okay, so here, so the point is that the XXZ does not necessarily has this property that you sum up to 0.
Ah, okay. Right. So it's a change of normalization to account
exactly,
for that.
Yes. Okay. So and then what one may want to do is like a natural generalization would be to allow more particles per site. Here I have this picture of this movie where like the RCEP or the TARCEP is used to study traffic jams, but if you have particles on top of each other, then there wouldn't be any traffic jams anymore. So that's okay. So but then you start studying this, and what you find is that you look at the integrable higher spin Hamiltonians, and what you find is that they are necessarily not they are not stochastic naively. And also, if you look for similarity transformations, this seems to be a bit more tricky. At least there's not this very simple relation that we've seen on the previous slides. And the other way around, if you come up with a higher spin stochastic model, so you maybe take your two-side Casimir and you insert these higher spin representations, then your Hamiltonian will not be integrable. And what we realized then in 2019 was that if you take non-compact representations, so Wemmer modules with the highest weight state and no lowest weight state, then you actually get Hamiltonians that are stochastic immediately. And so this I want to show a bit later. Okay. So let me, before showing you these new models, and they're not so new as we thought, I go and explain how this SEP now, or the ASEP, how this fits into the quantum inverse scattering method. And this we will use later on to determine the integrable processes for these non-compact representations. Right, so the starting point is the Young-Baxter equation. This we have seen now several times. And we are interested in a very particular solution of the Young-Baxter equation. This is for the SEP or the XXX Heisenberg spin chain. So this is just Z plus permutation, where P is this 4x4 matrix, EAB are the elementary 2x2 matrices. And this is a solution to the Young-Baxter equation. And I also introduced this diagrammatic language. Okay, R matrix is across, and then the Young-Baxter equation can be written like this. This we also have seen already. Okay, so when studying spin chains in the quantum inverse scattering method, the first thing one would do is to construct the spin chain monodromy. This is this product of R matrices in the so-called auxiliary space, and then I take a tensor product in this other space, which is called the quantum space. And this is then a 2 by 2 matrix in the auxiliary space and a 2 to the n times 2 to the n matrix in the quantum space. And it has this nice property that it satisfies the RTT relation, which is this equation here. So RMM is equal to MMR. So you can move these lines subsequently through this vertex here on the left, and then you end up with this picture. Okay. So, and then we can construct the transfer matrix. That's also quite a standard procedure that was developed by Fadeev and collaborators. So we take the trace of the monodromy. So we close here this auxiliary space. And as a consequence of this RTT relation on the previous slide, this one here, we find that the transfer matrix commutes with itself at different values of the spectral parameters. And furthermore, so then what follows is that when expanding these transfer matrices in the spectral parameter, then I find commuting matrices. And one of these commuting matrices is exactly the Hamiltonian of the XXX Heisenberg spin chain, or here now the Markov generator of the SEP, if you want. Okay, good. So then we'll conclude the T and the H have common eigenstates. And if I would like now study the spectrum of H, then I can also study the spectrum of T. And so this is a bit what the idea about this algebraic Bethe-Ansatz and the quantum inverse scattering method is. So how do these reservoirs fit into this framework? This was done by Sklianin. And he introduced this new transfer matrix, which is called the double row transfer matrix. So you have, again, a single monodromy here. Then there are these K matrices on the, well, two K matrices, K hat and K. These are responsible for the boundary parameters. And then there's another monodromy going backwards here on the right, and then you close this trace again. And the picture of this is that one here. So you have one monodromy going to the right, then you bounce at the wall. So these are these reservoirs. Then you go back, and then you bounce again at the other wall. So these K matrices have this diagrammatic expressions.
Wasn't there supposed to be a Z inverse somewhere?
Or minus Z, maybe?
Yeah.
Second half.
I didn't hear.
So the Z spectral parameter, I thought it was reflected by the wall.
Yeah, so sorry, that's, yeah, I'm cheating here a bit, but you can, I think if you flip these NA, so this is a bit like, then you get indeed this, yeah, this is not very nicely written here, it's true. But it's due to the symmetry, we can write it still like that. Yes, thanks. Okay. So now, in addition, so we would like these that these transfer matrices commute at different values of the spectral parameter Z and Z prime. And before we were just using the Young-Baxter equation, but now we have to introduce something additionally for these boundary K matrices, which is the so-called boundary Young-Baxter equation. And while for the Young-Baxter equation, you think about like 3 particles scattering, and it doesn't matter how they scatter. Here you have 2 particles scattering at a wall, and it shouldn't matter if the particle 1 touches the boundary first or if particle 2 touches the boundary first, if you think of time going upwards. Okay, and then if you write this equation, this is like this thing here. Again, here I'm not being very careful with the signs of the spectral parameter, that's true. But still the equation is correct like that. Okay, so and then these were studied already for the XXX or XXZ spin chain, and there's a most general solution, which is given down here. So you have 4 free parameters that in principle you can get rid of 1, so there are 3 free parameters. on each of these boundaries. Okay. So now I would like to match to my Hamiltonian of this open set now, and for this I just have to insert these boundary rates in a certain way, which I give you here. And then the logarithmic derivative of the transfer matrix, of this double row transfer matrix, will be the generator of the open SEP, as we've seen it before with these two boundary terms now. Okay. And again, the transfer matrix commutes with the Hamiltonian. And here, this is what I said before. Again, we can expand also the transfer matrix and we obtain commuting charges that I call QK. And this will actually become useful later on. Good. So let me now come to these non-compact integrable spin chains. So what we are changing now is that we're looking at highest weight representations of Wehrmann modules that do not have a lowest weight state. So here, this is the quantum space now. So I have my n sides, and each side, mi, can be occupied by 0, 1, 2, up to an unbounded number of particles. And then the generators of SL2, they act locally in the standard way. So S plus raises the particle number, S minus annihilates it, and S0 is diagonal. And we see here if S is bigger than 0, then this will never be 0, so you do not truncate the module. Okay. The Hamiltonian density has been obtained by Fadeev a very long time ago, but it is only, or is available in a very peculiar form. So it's written here, and it's very beautiful also, but let me explain what this S here is. So here a lot of is inside this curly S. So the Hamiltonian density is just the d-gamma function, so the derivative of the gamma function, or logarithmic derivative of the gamma function. And this S here, this is related to the two-side Casimir operator in the following way. So the two-side Casimir operator is roughly is S times S minus 1. So this is more or less the square root of the two-side Casimir.
Psi, is this a quantum dilogarithm or just a dilogarithm? Or
logarithmic derivative of the gamma function.
All right. Yeah, thanks.
Psi function. Yeah. Okay. Well, we will see a bit more what this psi will be, but yeah. So, okay. Right. So, well, okay. As I say here, you have to take is sort of the square root of the two-side Casimir operator, and well, this kind of expression was given by Fadeev. Then maybe in this non-compact representations first studied in high-energy QCD, then it appeared in n equals to 4 super Young mills, and then Derkachov was studying this as well. Okay, so let's see a bit more what this S is. So, and here we also see then that, okay, so what is this S? If I consider, so the Hamiltonian density acts on two sides of my spin chain. And so I have a tensor product of two spin S representations. And this decomposes into irreducible representations in the following way. So I have a spin 2S, spin 2S plus 1 representation, and so on up to infinity. And this operator S, this acts diagonally on the right-hand side of this equation. So, and it just reads off the representation label to S plus J. So this is diagonal on the right-hand side. No. And then you can compute the eigenvalues of the Hamiltonian density on the right-hand side here. And they are just the harmonic numbers. So this psi function reduces to the sum here from k1 to j, 1 over 2s plus k minus 1, which are the harmonic numbers. If I set s equal to 1/2, then I get 1 over k.
I'm not understanding your notation for the representations. I thought that the highest weight of the representation of the tensor product is 2s, but you have all these
I didn't.
representations. I'm not understanding your notations for the highest weight representations.
This one?
Yeah.
So like 2 spin S representations?
Yeah. So why don't you get a highest weight, a highest representation of 2s and then lower ones?
These spin S representations now do not have a lowest weight state. These are already infinite dimensional representations, both of them. So I'm using now it's a bit misleading because my S is positive. So the finite dimensional ones would come from negative S.
The sum is over k, right? So it's d2s plus k, I imagine. For the action of h.
Yeah.
Or is it a diagonal action? Or
It's diagonal, yeah, exactly.
Oh, it's diagonal.
So it's on the right-hand side here, on the irreducible representations in the tensor product, this h acts diagonally, so this s just reads out the 2s plus j, and the psi minus psi here, this just reduces to this simple sum, so the harmonic numbers.
And what happens if you multiply ds by ds prime?
It gets more complicated, yeah. But okay, so we are not doing this at the moment, but one could obviously also think about that. I think this is certainly a valid generalization that would preserve also integrability. So, but okay, the 2s turns into s plus s prime more or less, yes. Okay. So, right, so now we know how this H, the Hamiltonian density, acts on the right-hand side of the tensor product. But from this, we cannot really say if the process is stochastic, since we just have a sort of a diagonal matrix here. And what we would have to do is to go to the left-hand side of this equation here. And, well, we know how to do this. You use the Clebsch-Gordon coefficients. And then if you do that, you find the following action of the Hamiltonian density. So here H now acting on...
May I ask a question? I missed between the two slides. H is not a local operator. It's into the previous slide again. I missed. So you say that you define a spin chain. You states are tensor products of Mi. And then in the next notation on the next slide, the ds, your ds do not refer to a specific site. It's a state.
One side. So ds is one side. Yeah.
ds is one site.
Yes.
But when reading your equation, I have the impression that h is then acting on just on a single site.
So this is the density. So this is the h. The h is the sum of two h's here. Maybe that's.
Okay.
Yes, so yeah, exactly. So this is the density, and well, this I could go back, but okay. In the beginning, I was writing this, I think, sort of equation where you have to build as nearest neighbor interactions. Okay. Right. So let me show you what we get if you use this. Well, if you go to the left-hand side of this, acting on how H acts on the tensor product of two sides now. So with occupation number m and m prime, you have the harmonic numbers here. So this is now for s equal to 1/2, where this model simplifies significantly. So you have the harmonic numbers on the diagonal, and then I can already use this, or you remove excitations from the left side, and you put them to the right side, and it costs you 1/k. So you can remove all of the excitations that are on the left-hand side. So these are m now, so you sum over all possible numbers that you can remove. And then there's this, so it's symmetric, then there's a term that removes on the right and puts you to the left the excitations. So the harmonic numbers are this one here, and they are immediately related to this psi function. Okay, so here I write explicitly now this as a matrix for a given Magnon block, so a number of excitations. So the number of excitations is 2. So it looks like that. Well, this 1 over k is, so if k is 1, you get 1. If k is 2, you get 1 over 2. So this is this matrix. And you see that it's stochastic here. So we were already quite happy that without doing anything, we found a stochastic process. Okay. So here, this was the equation that I was just writing, sorry. So the Hamiltonian then you obtain by summing over the densities. And what we end up with is with a symmetric stochastic process without exclusion. And the hopping rules are the following. So you have a certain number, m, of particles at a given site, and k particles out of these m particles move with the rate 1 over k. Okay. Nice. So then you can switch on the S parameter as well, and you get something a bit more complicated. So there are these gamma functions that you can also turn into Pochhammer symbols, maybe. But what you see here is that now the M dependence explicitly appears also on the right-hand side. Before, you just had this 1 over k, and now it depends on the number of particles at the departing side. Okay, and again, this is a process. Okay, good. So this was more or less known. This was by Martins and Melo. They wrote this for the XXX spin chain, but didn't have this interpretation. So let's go on a bit so now you would maybe look at what, like we have this picture now, SEP, ASEP, and we have the harmonic. So there should be like a Q deformation of the harmonic. And this is what I would like to discuss next. And then we will add boundary terms to these processes. Okay, so Q deforming, everything what I've said before is not too difficult. It's just a bit technically involved. So you, instead of SL2, you have UQSL2, and so the generators satisfy these commutation relations, where you now introduce the Q number, that is this bracket here. Well, it's kind of standard, I think. And then the action of the generators is this one. So instead of, well, you see again just these brackets appearing, everything else remained more or less unchanged. Then the Hamiltonian density was found by Bitsko. Has again this the gamma function here, well, is also this is like a normalization that you can also forget about. And so this Q now is the Q deformed gamma function, which probably is defined on the next slide. S is related to the coproduct of the Casimir operator. So in the following way here. So the coproduct now is is a bit less trivial. So we have a Q dependence for the coproduct, which was not there in the rational case. And well, this is the Q gamma function, a definition that I'm using. And the D gamma function then is the logarithmic derivative of this Q gamma function. Good. So you look into the literature, and there are some Clebsch-Gordon coefficients available, and you look or you compute the action of the Hamiltonian density on the tensor product of two states, which is given on the slide here, which maybe is a bit overwhelming. But okay, it has again the same structure as before. So maybe this, I do not go too much into the details. Let's see if we, but okay, we know all the parameters. There's the Q, there's the M, there's an S. So this is all these parameters that we had introduced before. Okay, and like in the RCEP, so the XXZ chain is not immediately stochastic. We will need to introduce similarity transformation, which then yields a Markov matrix with the rates given here. So if you may wonder, what is this guy? So this is a Q-Pochhammer symbol here. So this is, I don't know if I defined this somewhere. Yeah, here, sorry. So I jumped over this definition. So this is the Q-Pochhammer symbol. Okay, right. So we ended up with these rates, and actually then looking into the literature, we found that this process was already studied. So what I've explained to you has already been known, but not from this algebraic point of view, I would say. So the rates were introduced by Powolowski without really referring to this XXZ spin chain and the algebraic structure. Okay, and then, well, following Powolowski, they were generalized to, like, you can, so Powolowski only considered like a TASEP type, and then you can generalize to left and right hoppings by Barak and Corbin. And in fact, the inventor maybe of this model, these two here, that wrote these rates for S equal to 1/2 in 1998. So that's maybe nice. Okay, so now we have all this algebraic machinery. So this is nice because we can introduce integrable boundary reservoirs. And this is what I would like to do next. Okay, so this was the picture that came up, well, summarizing what I said before. So we have this non-compact XXZ spin chain. Then, right, you can send Q to 1. You find the non-compact XXX spin chain, which is already stochastic. This was not stochastic, so there was the similarity transformation that then yields to this q-Hahn process. And okay, then there's a similar thing for S equal to 1/2, where this model significantly simplifies. Okay, so let's introduce these boundaries such that the model still is integrable. So, okay, we would like to add stochastic boundaries now for the rational process first, because there it's a bit easier to study these K matrices. So the transfer matrix, as I said before, is this double row construction of Sklianin. And we know what the R matrices in the monodromy are. They can be written in a nice way like this, using again this funny S matrix. So it's a bit difficult to work with this, but then you get used to it somehow. Right, and then the Hamiltonian would be the logarithmic derivative, so the integrable boundary Hamiltonian of this transfer matrix. But we do not know what are these K matrices. And in fact, we had to derive them first. So this was in 2019. So you look at a boundary Yang-Baxter equation that intertwines the fundamental representation with such a non-compact spin S representation. This is this one here. So we know these Lux matrices. They are just given the standard Lux matrices for SL2. And then we know the normal K. This was the most general solution that we introduced earlier. And we would like to solve this equation for this curly K. And with playing around a bit, you indeed find a nice way of writing this solution. So you can write it as a similarity transformation here. So this is like conjugated by e to the b s plus, e to the minus a s minus. And then there's a diagonal part, which is this bunch of gamma functions. This is a normalization. And here the gamma functions are just depending on the Cartan element. So a diagonal, then something lower diagonal, and then something upper diagonal. So this is the most general solution for arbitrary representations now. Okay, so this is purely algebraic, and such an expression was not known. The relation to these parameters that I had here, so the Q1, Q2, Q3, Q4, is this one here. So here I write everything in terms of A, B, C, and D. Okay, so this is, you have to believe me that you find this solution, and the other boundary is then obtained by symmetry, is something like that. Okay.
All right, what is little s on the
What
right-hand
is the-
side? Little s on the right, so you have A, B, C, D, but what is little s? In the expression for 1/2 left,
This
yeah,
one? No.
that one. That's your spin?
Yes, yes, yes.
Okay.
Yeah, and in fact, this is the normalization here, so this you can also forget about, but this makes it like sort of, so you expand these, so the idea is always, when I write these gamma functions, what I mean is always Pochhammer symbols, so that so S0 will have an integer spectrum. Then you can use the gamma z plus 1 is equal to z times gamma z, and then you truncate this product that comes out. So that's how I introduce this here. Okay, so we have this most general K matrix now, and we can now take the logarithmic derivative of this transfer matrix of the spin S representations, and ask that the resulting boundary terms, B1 and Bn, are stochastic. And this gives us some constraints on what these A, B, D, and C should be, which is given here. And well, at least from what we understood, it was only possible to keep one free parameter beta. So this is the new parameter now, which, as we will see on the next slide, is responsible for the insertion of particles at the boundary sites now. Okay, so these are the boundary terms now, the stochastic ones. We remove at the first and the last site, we remove with the same rate, it's the hopping rate in the bulk. So this is how we remove the particles. And then we insert the particles with these, according to this free parameter beta. So we have one beta for the left and one beta for the right. Okay.
Do the boundary parameters at all relate to the Kornwinder parameters?
Correlate to the?
So there's a relation between usually the system with boundaries to Kornwinder theory, where A, B, C, D. If you haven't matched, but you have one free parameter left.
Okay. I'm not sure I understand.
In your previous slide,
yes,
you solved for one free parameter between A, B, C, D, right?
yes.
Everything is controlled by one continuous parameter?
Yes.
I see, okay.
Yes, yes. Yeah. Yeah, so this you get if you just, you want this B to be stochastic, then this fixes you this. Okay, so then the story is a bit more complicated for the Q deformation. So far as I know, there's not such beautiful expression here. I think it's nice, this expression here for the K matrix in terms of the generators of the algebra. So this is sort of an evaluation map for the boundary K matrix, which I think is nice. So this is not known so far. There are some other results, partial results, maybe by Mangatsev and Liu and also by Tsuboi. So Tsuboi wrote an algebraic expression for triangular K matrices. And then Mangatsev and Liu, they wrote K matrices in component form, maybe for finite dimensional representations, but full K matrices. Okay, so then, well, but you can still take a shortcut. So this is called Sutherland's trick, maybe. So this you use usually if you would like to figure out if a Hamiltonian density is integrable. Then you take the Young-Baxter equation and you take the logarithmic derivative. And then you get some constraints for the Hamiltonian density. And something similar you can do for the K matrix. And this is how one can show that these, that these generalizations here of the ones that I showed you on the previous slide. So these now have this Q parameter, which, sorry, I should have maybe mentioned this much earlier. So Q square is equal to gamma. So this is now the Q deformation of these boundary conditions that keep your model integrable. Good. Okay, so now we have these incomplete, like we have the, so like the open RCEP and the open SEP, we have now these open non-compact Q-deformed model and this rational case of this. And then we started to study this, and the first thing that we looked at is the steady state. Okay, so usually in the ASAP, so this was solved maybe in 1993, and I should have maybe put Günter Schütz here as well, using the matrix product ansatz. So the idea is a bit the following. So you're looking for a state on which H, your stochastic Hamiltonian, is equal to 0. So this is called the steady state, this thing. Okay, and the ansatz is the following. You write a tensor product here of these x's, and x's are two vectors containing matrices, or well, operators E and D, and then you sandwich this with W and V. So this thing will then be a 2 to the n vector after doing the sandwich in this operator space, this E and D's live. Okay, so if you have not seen this before, it's no worries. We are not using this method immediately, but this is how you would conventionally maybe solve the ASAP nowadays. Okay, so the E's and D's, they satisfy some algebra. This is this one here. This can be more or less also reformulated in terms of Q oscillators, I think. And at the boundaries, you have these conditions here. And these relations, they allow you to evaluate this thing, and then you find the steady state for a given length, n. So Z is just a normalization. Okay, so but in our case, it's a bit more complicated since we do not have only E and D. We have we have infinitely many of these operators. So we decided, or we were looking for an alternative route that I will explain on this slide. Okay, so this is a bit tricky to explain, and maybe one slide is not enough, but let me try. So this is now for the rational model. And what I did not explain to you is that there's a dual process which is purely absorbing. So you can also say that there's a similarity transformation that brings your stochastic Hamiltonian into a triangular form. Okay, so if you have a triangular matrix, obviously the spectrum. So first you're using a similarity transformation, so your spectrum will not change, going from the process to this triangular version. And then you can even go further and you go to a completely diagonal boundary terms, which again have the same spectrum, since the triangular parts now of my boundaries will not even affect the spectrum. So this is like a standard thing. I think if you have a triangular matrix, only the spectrum will not change. Right? And what we were able to cook up is a similarity transformation, which is non-local. So this contains this very complicated, or not too complicated, matrix W delta. So this one here packages together. This is the inverse. And there is a relation now between the stochastic Hamiltonian with boundary parameters beta left and beta right to the Hamiltonian of equilibrium, where I set beta left and beta right equal to beta. And in this particular case, the steady state factorizes, and we have control about it. And we can also use the algebraic beta ansatz here, actually. Okay, so what are these W deltas? A way to determine this is using this transfer matrix that we constructed. And you end up with this expression here, the sum from 0 to infinity involving this Q plus K. And this Q plus, this comes out of a charge of the transfer matrix. So exactly this one I get when expanding the transfer matrix. Okay. Good. So this leads a mapping then between all the eigenvectors of H and H equilibrium. And for the spin chain people, maybe it's a mapping between the H and a diagonal, a spin chain with diagonal boundaries, which we know very well how to study using beta ansatz. Good. So then we know explicitly the steady state in equilibrium, and we can just use this transformation W now to obtain the steady state in non-equilibrium. And this is written on the slide here. It's a bit tricky. So this is the steady state. So it's a sum over some complicated things. So F here are some factorial moments. And rho n is related to the, sorry, I was mixing notation now. So this was related to this beta left and the rho 1 to the beta right in the following way here. Okay, so this is like, and then, well, you see it's completely explicit now, only written in terms of sums and products. So this is sort of, there's maybe an advantage even to the matrix product ansatz in this respect, if you are looking really for the probabilities. Then this formula maybe is more efficient. You can just put it on the computer and evaluate it, and you do not have to use this algebra. Okay. I have 5 minutes. Okay, that's probably enough. So let me tell you how the story continued now a bit. So there was some work then by these people here, Carinci, Franceschini, Gabrielli, Giardina, and Scargo. Okay, and so they managed to repackage, okay, and then there was a follow-up work where we managed to repackage this formula here, this complicated sum formula, into a rather nice looking integral formula here. So this you can obtain by using the integral representation of the beta function. The beta function more or less appears here as a fraction of gamma functions. You can already imagine that there might be a gamma function somewhere. So then, and then you can actually take these sums and you end up with a, well, a more beautiful expression, let's say, but okay, the sums are now encoded in the integrals. And well, what is exciting about this is maybe that you can reinterpret this as a mixed measure. This is something I'm not so familiar with.
Sorry, may I ask a very amateur question? So this steady state, this is just a matrix coefficient in representation of U of SL2, right?
It's a matrix. It's like it's a state.
Well, pairing of two vectors in.
So it's a particular eigenvector of my transfer matrix.
Sorry, what?
Is a particular eigenvector of my transfer matrix.
But you pair it with something.
Sorry?
You pair it with something, don't you?
What do you mean pairing with the?
Well, you have M and psi.
You have a bracket. It's a matrix element.
Ah, okay. Sorry. Yeah. So these are just the components of this vector. Yes.
And purely from a representation theoretic point of view, how do I know that? So this is an eigenvector of what again?
Of the Hamiltonian.
Oh, I see.
Or of the transfer matrix, or yeah.
Okay, got it.
So this is yeah, it's a
Thanks.
particular eigenvector of the family of commuting operators. And yeah, sorry, I'm using this physics notation that I use brackets. Yeah, that's I was always told not to do it, but okay. So these are just the components then, and yeah, you could also, yeah. Okay.
That's not a matrix integral, right? Because it's only between neighbors, the interaction theta I minus theta I minus 1.
Matrix integral in the sense of?
Yeah, usually you have very similar formulas where the theta I are eigenvalues of random matrices.
Ah, okay.
But usually theta I interacts with theta j for all I different from j. Whereas here, there's...
Okay. Maybe if you wait on the next slide, then yes, it maybe clarifies a bit more. Okay, so for me, this expression came a bit, well, out of the blue, let's say, but if you look a bit into the literature, also Derkachov already wrote R matrices in these type of representations as integral operators. So then maybe this makes a bit more sense. But so where is the matrix product ansatz? And this you actually can obtain if you look carefully at this expression. So the point is that you can write now this mixed measure, I call this, as an integral product state. So you define integral operators, xm. So m goes from 0 to infinity. They take a function h and produce a variable p. So you take this function h of t, and your new variable is the p. And this then plays the role of these E and D of the matrix product ansatz, but now the M, so we have infinitely many of them. And you can then, if you look carefully, you can disentangle these integrals here and this product in this form. So you start with a function W. This is just this one here. Then you act once with your x, here, the integral operator, and then you continue and continue. And then in the last step, you just identify P with beta left. So this is the matrix product structure. And I'm not sure this, maybe this, but okay, we can see later on. Here you see that it's always P and P, like there's no mixing between several sides, I would say.
What is the symbol, the multiplication symbol correspond to?
This one is just, yeah, like
convolution.
Implying, yeah, this convolution. Okay. So, but then, well, we are nearly there. The last thing now is to extract maybe matrices, if you like. So this you can then find by acting with xm on polynomials t to the k and picking powers of t. Well, so then you see how these x's act on polynomials, and this will be then the matrix. So this is then, everything will be a matrix product ansatz again. Okay, so my time is up. Let me just tell you that there is a generalization for the Q deformation, and the formulas are very, very similar. So here you see, well, this is this operator x, and you have some q-Pochhammer symbols appearing. But the main difference now is that this integral is replaced by a Jackson Q integral. So this is, but everything else more or less stays actually the same. So I found this very cute that you just introduce the Jackson Q integral. And well, in fact, even for s equal to 1/2, you don't see any difference in the formula, just that you replace the integral by a Jackson Q integral. Okay, so that's it. Yeah, so now maybe for the future, we would like to compute some observables. Then, well, the mapping of the open q-Hahn to equilibrium, like even the ASAP, we do not know how to map this to equilibrium. And then there's room for generalizations of higher rank models that were studied by Kuniba and collaborators, and also then recently by Mangadzeev and Kolyaskin, they found some K matrices here. So this is certainly nice too. Thanks.
Sorry, one more question. These representations of SL2 that you were considering, do they integrate representations of the group SL2R, like in Dergachev's papers?
I wouldn't know. You mean?
And these were representations of the algebra.
Yes.
But in principle, it may happen that there's some representations of the group SL2R that when you differentiate and you get representations of the algebra, you recover those that you considered. Is that the case here?
I don't know. Yeah.
Thanks.
What are these? I mean, I have this. What are these representations? How does SL2 act on them?
So is SL2R?
Are they cyclic?
Sorry?
Are they cyclic?
No, but I mean, this isn't it? So, I mean, doesn't this reply to the question already? So I wrote explicitly the module, no? This one here. So
did you say that you kind of reproduce a standard matrix product, matrix representation?
Yes,
What
so
do
this
you
was
mean by the standard? Is it representation related to ASAP, or this is just a some kind of a representation in the form of matrix?
okay, at the moment this is just some this is very preliminary work here, so this is a bit still a work in progress. But so these matrices, we actually do not really know how they do relate to the ones of the ASAP. So in the ASAP, I know that there are different ones that maybe play a particular role. Here, we have not much control of it. You see that also in this bulk, there appears beta right, there appears no beta left. So it's a bit of a strange basis maybe that we are, so there should be maybe some nice similarity transformations to make it look more like the conventional ones from the ASAP.
Okay. And one more question. Have you tried to represent some physical quantities in the form of, in the language of matrix product?
Not yet.
No, not yet. I'm curious.
That's all.
Maybe next time. Thank you.
Thanks.
I have two questions. The first is something maybe I missed. Your parameter S, it's a real parameter?
Yeah, it's real, and yes.
Is there a range? So because at some point you
bigger
take
than zero, yeah, it must be bigger than zero. Otherwise, you do not, the rates will not be. So for negative half integer, the module truncates, becomes reducible, and you get finite dimensional representations. And I think also for non half integer negative, even the rates will like oscillate, and you get minus signs, plus signs, and so then this breaks down the stochastic.
And what is special about S equal 1/2?
So this was just that the rates. Well, okay, well, what is special about it? I do not know, but so these rates here, they lose the dependence on the number of particles at the departing side. So you just get 1 over k. So
Okay, so this is the model you describe is S equal than 1/2 here.
no, so most of the results are valid for all positive s equal to 0, bigger than 0.
Okay. And my other question was about the matrix on that. So in the original approach of Derrida, Evans, Hakim Pasquier, they start from algebraic relations satisfied by D and E. They don't really care about the representation, etc. And here you proceed in the other way. You first have the steady state, and then you find matrices which, but you don't know relations for these. The equivalent of a DE relation, you don't know them, right?
We know them, so
you know them?
They are just but
They're not practical.
They are not very indeed, because before the Hamiltonian was just something like a 1 minus permutation, so like 2 terms, which made the commutator. But now the Hamiltonian has many terms, so it will not just be 1 commute. I mean, maybe you can reshuffle things and find a nice.
But there is no way to check stationarity out of these relations.
Well, I mean, this is just complete. I think it's just complete. Everything is more or less the same as before, but so the left-hand side where there's the commutator of the. I mean, how do we? Well, okay. For us, we check stationarity from mapping to equilibrium. We know from there you have a path so that I mean, but you could maybe recheck it as well. But yeah, it's tricky. The algebra is more complicated. It looks to me. Yeah.
Okay. Thank you.
Not very satisfying answer.
Okay, maybe we'll leave the rest of the questions for the break time. So thank you very much.